So up at the top, there's a little bit of just fill in some notes here about things that you think. I don't want you guys to worry too much about problem number one because there's not going to be like an essay question on the test. So here it says describe key characteristics of all chemical reactions, including the role of energy. Explain how a balanced equation represents those features. Include an example. So one thing about key characteristics of chemical reactions is that you'll be able to see evidence for them. So one of the very first things that we did was a series of demonstrations with different things. And what we saw was stuff like produces a gas, or we saw bubbles. So produces gas or bubbles. It may change temperature. It may get hot or cold. It may produce a precipitate. We may see color change. The color changes that we saw were when the copper went into the solution, it made the solution blue, or when we put it in fire, we saw green. We saw green flames. That was different than our usual flame. So we would see evidence of those things. In terms of the role of energy, you're either going to use energy to break bonds, or energy will be released when new bonds form. This isn't enough. The presence of bonds breaking or forming isn't enough to say if we're going to have an endothermic or an exothermic reaction in and of itself. But should we put this? Because things happen sort of at different rates, and so the balance of those is what sorts that out. We'll talk a little bit more about that later, but at this point, that's all that you need to know. For something to be spontaneous, for a spontaneous reaction, the reactants have to have more energy than the products. And because it asked me for a sample, I picked one from the next page, which was one that we actually saw in our demonstration. That if we consider the reaction where we take sodium carbonate and we add hydrochloric acid, when we did this one, we noticed that there were bubbles produced. And the bubbles were CO2 plus water vapor, and we also got salt water. But this also produced some energy. Also got a little bit warm. And so we can also think about energy as a product or a reactant. So if something is going to produce heat and release it into the environment as a product, if it takes energy for something to happen, it's going to be something that belongs on the reactant side. So those are a few notes to go in there that answer that question. Don't worry about this too much. Okay, applying this model to things. So if we have this reaction below that's given to us, we need to balance it. So if we were going to try to balance this so that we had the same number of things on each side, we could take a look at this and say, okay, this molecule, I'm going to call it A, B, C. This molecule, I'm going to call B, and then 2, because there's 2 B's there, and then D yields this molecule, AB3 plus C2D4. But this isn't balanced because if we look at it, especially with this one, there's 2 C's here, but only 1 here. And there's 4 D's, but only 1 D on this side. And so if we needed to balance this, we would need to add more stuff. The best way to do this is to use these current molecules, if that's at all possible. What I did is I took a look at this one here because it indicated I needed another of this one with BAC because the other molecule does not contain any BAC. So if I make another BAC molecule, stick it in there, now I have enough C's on both sides. In order to have enough D's on both sides, I'm going to need to add 3 more of the molecule that has D in it. So B, D, B. So there's 1. 2, 3. Okay, so now I have all this, but now I have way too many A's and B's. I've got 2 A's and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 B's. Thought that I had this balanced, and now I'm not sure that I did. Oh, no, I'm okay. I'm okay. Yeah, I'm okay. 2. Wait a second. Hold on. Time out. Dang, I thought I had it balanced, and now that I'm looking at it, it's not balanced. Yeah. I know, but I find that very unsatisfying. Like, the easiest way you could solve it is just to create a new molecule. So, I mean, yeah, it doesn't say that you're not allowed to do that. It says add an additional reactant, and there is space to propose a reactant that had not been there. It's definitely the easiest way to get out of it. But like I feel like it's unsatisfying and that I want to balance it. And I'm having like basic algebra problems. Hold on. Hold on. So we know that we have to have a 2-to-4 ratio of these two. We know that. And if we go with 2-to-4, whatever this is, it has to be this one. So this, and this has to be 2x, and this has to be x. And then it should work. Why doesn't it work? 1 plus 2. I just can't. I can't. We have to have 2 of these. So then it has to be 2, 4, 2. Why doesn't it work? Curse words. 2, because I got 2 A's and 2 A's, and then 2 B's. See, this is my problem. And then there's 2 B's here and 8 B's here, but that's 6. Why did I think this was okay before? I think I'm going to let it go for a while. Anyway, so one way you can do it is this. Dr. Miley's not super excited about that, but whatever. We'll roll with it. So I know. Either that way or that way. There is a problem like this on the test. I'm just going to let it go. Okay, so, and then this is write the balanced equation for this reaction. So those of you who are on like team invent a new molecule, it would look like this. ABC plus B2D plus the new molecule, which looks like this, CD3, yields AB cubed. I don't know, AB3. It's not cubed. Don't say cubed. Which of these molecules will be called reactants? The ones on the tail end of the arrow. So that would be ABC plus B2D plus CD. Oops. CD3. Maybe when I'm at my son's appointment this afternoon, I will figure out how to balance it. That would be exciting for me. Okay, do we have any other questions about the first page? It's not supposed to be the complicated one. Yeah. Go ahead, Tammy. The reactants are the before and the products are the after. The products are what's produced. So whenever you see an arrow, the stuff that the arrow is pointing to is the reactants. And the place where it came from, sorry, is the products. And the thing where it came from is the reactants, because they're going to react together. So this side is always the reactant side, and then this other side is the product side. This is going to make me crazy. I'm going to figure it out. Mm-hmm. Yeah, that style thing. Dang it. Okay, I'll figure it out later. All right. For page number 2, I'm going to do this part a little bit quick, so you guys can stop me if you have questions. For 3A, if you balance these, it should be 2, 1, 2, 1. For B, 2, 3, 2, 2. For part C, 2, 1, 1, 2. For D, 2, 2, 2, 1. And on all of these, this is the reactant side. Side over here is the product side, the stuff that's produced. Then for the next ones, solid potassium chloride is going to be KCl3, sorry, ClO3. ClO3, and that's going to be heated and then produce oxygen and potassium chloride. This, by the way, is a salt that you can buy at the grocery store. It's for people who can't have sodium. And to balance this, you would need 2 potassium chlorates. You get 3 oxygens and 2 potassium chlorides. For the next one, zinc plus lead nitrate. And you guys are going to get that polyatomic ion sheet. It's like the decoder ring of science class. Your coefficients for this should be 1, 1, 1, and 1. And just for fun, this first one is a double replacement reaction. The second one is combustion. The third one is double replacement. I always think about water as HOH, and that kind of helps with figuring out where it should go. That's where this hydroxide came from. So this one is going to be a double replacement. This last one here, remember this guy here is HOH, so we've got sodium, HOH, and we end up with the hydroxide on the other side. So the hydroxide is leaving. So this is a single replacement. Any questions about any of those? LOL charts. All right. Problem number 4. When 3 molar hydrochloric acid, HCl, is added to solid sodium carbonate. Oh, this is the one that we did. We just talked about it. Sodium carbonate. It's going to yield carbon dioxide plus water plus salt water. So we've got this dissolved into its ions, right? It's positive and negative ions into a solution. Everything else is, this is a gas. This may be a gas too. And to balance this, we're going to need 2 hydrochloric acid, 1 of sodium carbonate, 1 of carbon dioxide, 1 water, and 2 sodium chloride. That's our reaction, and it's balanced. Our reaction says the contents of the test tube immediately starts bubbling, it produces a gas, and gets warm. So that tells us that the thermal energy increases. Now we have to figure out what's happening with the energy. We have reactants. So the reactants is when we have just the stuff at the beginning. And then the products, which is the bubbles in the salt water. And then the products after some time. We're told that our products are warm. And so what's going to happen is the reaction is going to make us have something that's warm. So we're going to go from room temperature to warm. And then later our products are going to come back down to room temperature. So we know at least that if we start out with some thermal energy, that our thermal energy will increase. And then later it will drop down because that energy is lost to the environment. Energy that's lost to the environment will always be lost as heat. So this is our heat leaving the system. Bye-bye, heat. It's gone. Question is, where did it come from? Well, if we take a look at this, we can see that there's a chemical reaction happening. So if we start with our chemical energy at just, our middle of the road chosen number, that's where it has to come from. So come from here, get transferred over. So we're going to have less chemical energy. And it's going to stay down. There's no reason that it's going to go up later because chemical reactions will proceed to something that's more stable. Also, because our energy left the system, we can actually write that as a product as well. So you have an exothermic reaction. When you see these little graphs down here that say progressive reaction and then chemical energy, one way to think about those is think about the first graph as time A, the second one as B, and the third one as C. And here we want to focus on our chemical energy. So if I just put those across my graph, what I'm going to do is kind of look at where my chemical energy is. Here it's at a 2. So I'm going to put a dot there at a 2. For time B, it's at 1. It's dropped. And then for C, it's still down at 1. And so I can draw a graph by connecting those dots to indicate that my chemical energy drops between time A and B and then stays low. What questions do you guys have about our LOLOL chart? By the way, if you think that one of these accounts doesn't change, it's okay if you just don't draw it. It makes your diagram a little bit simpler. And with it not being there, I'm indicating that there was no change, right? That's what the point of those are. It can be either no change at 2, it can be no change at 0, just as easily.
What is energy
reaction? If you have to add fire or heat to make it happen, because it's always going to go in and out of the system as heat. So it can go in because we had to light it on fire. Or it can go in if our thermal energy gets used for a chemical change. And we would have evidence of that because heat has to go into the system to bring it back up to room temperature. So if it says it gets cold, that's a clue that we're going to have heat energy going into the system. Only if it's because you're boiling it. This is because it's producing a gas. Yeah, no problem. I'm just checking our time. Okay, so number 5. As solid sodium nitrate dissolves in water, the resulting solution cools. This is a clue about thermal energy. So we need to write, let's see, our ammonium nitrate, NH4NO3, dissolves in water. So when it dissolves in water, that means it's going to dissociate into its ions. So we're just going to split it up. Nice thing about that is that it's pretty easy to keep them balanced. We won't have to do too much balance work. Now it says that it cools. So if it cools, that means that it's going to absorb energy from the environment. And we're given LOLOL charts here with reactants, products, and products later after some time. So what's likely happening with our thermal energy, because it's cooling, is that we're going to start out at whatever value we want to pick, and then it drops down below room temperature, and we're going to put energy into the system to bring it back up. So we have to figure out what's happening that's making it drop. Well, the thing that's happening, we're not having a phase change. It's not boiling, it's not freezing. What's happening is there's a chemical reaction happening where we have a solid molecule and it's splitting up into its ions in solution. So that thermal energy is going to chemical change. It's breaking that molecule apart. Oh, sorry, this needs to start out here. Sorry. And so over here will be 3. And then there's no change. There's no energy going in or out of the system. It's all just energy that's within the system changing it. So we end up with something where the final pieces have more energy than the reactants did, and that stays high. Now, if the water all evaporates out, what will happen is this will start to form crystals and release energy into the environment. That's what happens when you form bonds. That happens with rainfall as well. When rain droplets form, they're not ionizing like this. They're just water molecules that become associated with each other. And as that happens, it releases energy. It's kind of an interesting thing. So for our chemical energy change situation down here, if we do the same thing, this is time A, time B, time C, and mark those down here, A, B, C, 1, 2, 3, 4. Our first one has 2 blocks for chemical energy, so I'm gonna put that at 2. And then the last 2 each have 3. So on this one, if you compared it to the prior one, we've got our chemical energy actually increases. All right, then lastly, types of reactions. Remember, there's only 5 different types: synthesis or combination, single replacement, double replacement, decomposition, and combustion. So when we fill these guys out, we've got 2 things, magnesium and iodine, and they are together as a molecule, and then they split up into 2 different solids. This is a decomposition reaction. The next one has a hydrocarbon. It's something that's got carbons, hydrogens, oxygens, along with oxygen gas, and it produces CO2 and water vapor. This one is a combustion reaction. Next, we have calcium chloride with sodium carbonate, and then they switch partners to calcium carbonate and sodium chloride. So this is going to be a double replacement. Next up, we've got carbon monoxide plus chlorine gas produces this. Oh, I forget. He's got a special name. It might be chloroform. Anyway, so we've got this molecule here. And those things are combining together. So that's going to be a combination or synthesis reaction. Be careful if you decide you're going to abbreviate these, because combination and combustion start with the same letters. So you want to make sure you put enough information there that I know what you mean. Lastly, zinc plus copper sulfate yields copper plus zinc sulfate. This is the sulfate switching partners, right, from the copper to the zinc. So this is going to be a single replacement. You guys have any questions about those?